to something more related to field theory, but I decided to stick with this topic. Of course, T-duality comes from field theory, but the problem I like to talk about is really a problem, old problem in just topology. And the point is, I just want to essentially promote the idea that physics is useful in mathematics, and using these ideas for T-duality from string theory, you can actually shed some new light on this old problem of computing K-theory for very simple spaces, namely compact Lie groups. So just to set the stage, let me remind you, just give you a brief sort of historical background to this topic. So G is a compact one-connected, so connected, simply connected Lie group. Let's call n the rank of G. So it's semi-simple in particular. So as most of you knew, one of the first invariants you want to compute is singular cohomology. One of the first spaces you want to apply it to would be these sort of spaces. So this was started early on in the 20s by Cartan and by Pontryagin and Brouwer, and it was finalized the rational cohomology. It's computed by Hodgkin and Samuelson back in 41. And it's a very simple structure. The rational cohomology ring is, here you can even drop the simply connected assumption, is an exterior algebra on n generators, and the degrees of these generators are related to the exponents of the group. So Mi. Of G. Now if you pass from rational to integral cohomology, things get much more complicated. So integral cohomology has torsion. And a lot of effort went into computing these torsion subgroups. So again, a lot of prominent mathematicians that worked on this problem for various special cases, classical groups, exception groups, and so on. And let me just mention maybe just one reference is back from the 80s. So it looked, the calculation would look like it was sort of case by case. And there is actually a very sort of general procedure for computing these torsion subgroups, and it was worked out by Katz in the 80s. So I believe it's 85. He essentially these are related to the basic Weyl invariance over the rationals and certain subsets of these invariants. So he provided a general procedure for computing this. These P torsions. Subgroups. So now, if in light of Hopf's theorem and what we know about the integral cohomology of a compact Lie group, the following result is quite surprising. So this was Hodgkin's PhD problem, essentially, was to work out the K-theory ring of compact Lie groups. So and the result is very surprising. So this is it has no torsion, so it's isomorphic to an exterior algebra over the integers. On n generators again. These are all correspond to the fundamental representations of the group. So now the question, what is this actually telling us? It's if you apply the Chern character, you get a rational isomorphism. So essentially, Hop's theorem is already computing the K3 ring rationally. Gives so the content of Hodgkin's theorem is two pieces of information. The first is that so Hodgkin's theorem tells us that the K3 ring is integrally torsion free. So and it also tells us the multiplicative structure. So knowing the multiplicative structure of a rational doesn't determine the ring structure integrally. So it tells us the ring structure. And so this talk is essentially about going back to this theorem and giving an alternative proof using ideas of dualities that we heard a lot in the previous talk. A different kind of duality, though, not the electromagnetic, but this sort of topological T-duality. So again, let me give a bit of history on this theorem. It's kind of a interesting. Actually, there are already several proofs out there. So of course, Hodgkin himself, that was his PhD project, is a mastodontic piece of work. I'll remark on it in a second. But in fact, before he published his paper, Atiyah already worked out the ring structure under the assumption that the K group is torsion free. So Atiyah in I believe 66 computed the multiplicative structure on modular torsion, or assuming that the K group is torsion free. And he devised a very, essentially the idea was to pass to cohomology, so he applied the Riemann-Roch theorem to do the calculation in cohomology. And he, in particular, he used the following map, this very natural Weil map, which sends so essentially he passed the cohomology, and he also transferred the problem of computing, doing the cohomological calculation, to doing the cohomological calculation on this space. So this gives you a pullback map on K3. And I mentioned this because this space is going to sort of come back again in this talk. So this gives you a map from K3 of G into K3 of this product manifold, but it's not an isomorphism. So the point is that T-duality sort of tells you how to make this an isomorphism. So that was Atiyah's contribution, and Araki, the same year as Hodgkin, used Atiyah's result together with working out sort of the differential Hopf algebra structure on the K3 ring and the Atiyah-Herzberg spectral sequence to work out the torsion freeness. So he gave a proof of freeness. And as I mentioned, the full result is due to Hodgkin, 67, and his proof. Why I said is a remarkable proof is that he used the information we know about integral cohomology and applied the Atiyah-Herzberg spectral sequence. So he computed the K ring by essentially using the information from cohomology and showing that the differentials miraculously cancel all the torsion. So and also computed ring structure. So use Atiyah-Herzberg spectral sequence. Kill the torsion coming from cohomology. It's a very, and the other thing is that since you start with cohomology, you have to do this sort of case by case. So it's a almost 40-page paper that works out the full result. And all right, so this is the background. The goal today is to give a new proof of this old theorem. At least sketch the proof. I might not get through all the details. Using T-duality, and this has two merits. The first thing is, as you see in a second, the torsion freeness is completely manifest from the get-go. So you'll see immediately why you don't have torsion in the K-theory ring, and the multiplicative structure also is sort of, the idea is to do is Fourier-Mukai transform. And the multiplicative structure comes from the convolution product on the other side. So it's again a very sort of nice picture. And right, so the merit, I would say, is it's quite short proof, but also the merit is that I'm put it in quotation marks. It explains why there is no torsion. At least gives an alternative perspective on this. Right, so again, I was hoping Konstantin would have given his original talk, because then he would have covered a lot of the background material going into this talk. So again, I'm assuming everyone at least hopefully knows something about twisted K-theory. It turns out we don't actually need the explicit construction of twisted K-theory. We just need to know that something like that exists. So let me just start by saying something about T-duality, and then try to sketch the proof of this alternative proof. Topological T-duality. Let me again assume no one has seen this before. So let me just start by doing a little toy example, and then explain how we can extend the picture. So the input is you have a real n-dimensional vector space. Pick lambda full rank lattice. So this gives you a torus, and a torus comes accompanied with a dual torus, which is you just dualize the vector space on the lattice. And the dual torus, of course, has a very nice interpretation. You can view this as a local system on the original torus. So these are pi 1. I feel like the Pontryagin dual of the fundamental group. And this is the fundamental group is this is the universal covers, this is the lattice, and let me write it out, introduce a basis. Call this T1, Tn, and same thing for the dual torus. Tn. Right, so as soon as you have a torus and a dual torus, or more generally in algebraic geometry you would have a abelian variety and dual, you can write the suggestive diagram like this. Take the product and projections to each factor, and now there's a natural universal line bundle sitting on top here, the Poincare line bundle. And the defining property is that if you restrict P to point on the torus, say, cross T hat, that corresponds exactly to the flat line bundle defined by that element, right? A point on the torus gives you a flat bundle, line bundle on T hat, and vice versa. So, say, on T hat defined by T, and same thing if you restrict to a point on T hat. And you have a natural connection, and the curvature form is just a standard symplectic form on T cross T hat. So right. And now that what you can do is, of course, the T and T hat here, we're in the smooth category. So this is, or they're just smooth real manifold. So these are isomorphic spaces. So you don't expect to get anything interesting. But you can still try to write down the Fourier-Mukai transform in this very naive picture. So the Fourier-Mukai transform is the usual operation. You pull back, you tensor, push down. And that gives you an isomorphism with a degree shift. T hat, which is P hat. You pull up, you tensor with this line bundle, and then you push down. So again, this is not very exciting since these K groups are the same. So the idea is to enhance this picture, and why I'm talking about this, going back to the previous discussion, is that picking a maximal torus inside a group gives you a natural torus bundle. So the idea is that we want to enhance this picture to go from a single torus to a family of tori. In particular, for our purposes, it's sufficient to work with principal torus bundles. So the idea of T-duality is to enhance this picture. So extend to a family of tori. And this is possible, but you need some additional structure. So let me write it here. So you need additional structure for twisting a gerb in the local system for a K3, if you like. So the picture is the following. Let me maybe just quote the result. So there's several people who contributed to this sort of topological T-duality. In the rank 1 case, it was done by Bautnik, Epsilon, Matai, and also Bunkin Schick. And the picture is the following. You have a principal torus bundle. So you have a torus bundle, a dual torus bundle. You have the correspondence space, fiber product up here. And now to get an interesting T-dual, you need to equip the torus bundle with a gerb. So let me. So this is defined by its Dixmuir-Duarte class, and the condition is you say that this pair xg is T-dual to x hat g hat if you need two conditions. The first is that if you take these gerbs and you restrict it to each fiber, it should be trivializable gerb. So the first condition is that the restriction to fibers are trivializable. And the second condition is that if you pull up the gerbs to the fiber product, they should be isomorphic, but the isomorphism can't be an arbitrary isomorphism. You want to essentially replicate what happened in the trivial case of single torus. It should be the Poincaré line bundle. So you want the pullbacks P hat pullback of the gerbs to the correspondence space should be isomorphic, where P is, if you like, is a twisted Poincare line bundle. So it's not a line bundle anymore, but it's a rank 1 element in a line bundle in the twisted K-theory upstairs on the correspondence space. Right. So the question is whether you can actually find such gerbs satisfying those conditions, and essentially cohomologically, if you forget about torsion, the condition is on the Dix-Medullari class of the gerb. So you have a degree 3 integral cohomology class on X classifying the gerb of the isomorphism, and the condition is that for the gerbs to be T-dualizable is that the Dix-Medullari class only has essentially one leg on this fiber. Like if you decompose think of Drom forms, you decompose your 3 form into invariant forms by averaging over the group. It should be a form with a basic form plus a form that has one component on the fiber direction. So that's essentially the cohomological condition on coming from that definition. Right. So the idea is now to apply this theorem to our case of a compact Lie group. So the theorem is that this compact Lie group with no twisting, so with a 0 gerb, is T-dual to the trivial torus bundle over the flag manifold, but with a non-trivial twisting. And something I didn't mention is that this picture, once you have a diagram like that, you got an isomorphism in ordinary K-theory, and when you have that diagram with a principal torus bundle, you get an isomorphism in twisted K-theory. So we have that's the first statement. The second statement is that you have an isomorphism here, which is again the same thing as before. It's a pullback tensoring with the twisted Poincare line bundle and then push down. But the difference is that we need to introduce a local system on our for our K-theory groups. So essentially the thing that Atiyah missed, I guess, back in the 60s was that he was looking exactly at the map from for this product into G, but to achieve an isomorphism you need to twist your K-theory. So that's maybe the big insight coming from this T-duality picture, is that you can actually sort of trivialize your torus bundle, but the price you pay for trivializing it is to pick up a local system. So the topological information of the twisting goes into the twisting of a gerb, by a gerb. And then again, this is it's the same thing. Again, twisted K-theory element. It's so you view this as a twisted K-theory element now, and then you push down in twisted K-theory. That's the operation. So now just philosophically, usually if you introduce a twisting in K-theory, life gets much harder. So what twisting usually does is to introduce even more torsion into K-theory. So a priori you wouldn't expect this to be very helpful, but it turns out even though you twist your K-theory, what you've done is to trivialize your torus bundle. And the idea is that if you want to apply spectral sequences, it's nice to have a product because you can apply it in 2 different directions. And the idea is that is to essentially compute this problem of Hodgkin, his PhD problem, by going back, essentially doing the idea of Fourier transforming the problem to another space and applying the spectral sequence on this side. So By the way, any questions? Am I assuming too much about GERB? So stop me if you have any questions on anything I'm saying, including. So I haven't defined this twisted K theory. Some of you haven't seen this before. I'm assuming most of you are experts on this topic, but the actual realization of this twisted K group is not relevant. We're just going to do some homological algebra. So what I'd like to do in the remaining few minutes is to just sketch how the calculation goes, and in particular point out is this mystery with torsion, how it's very sort of manifestly torsion-free if you compute it on this side. So the idea is to compute the twisted K theory ring of G by working on this side instead and transporting the information back to with the Fourier-Mukai transform. And let me just point out another thing is that while the K theory group is a ring, when you twist it, you're stuck with a graded abelian group. In general, you don't have a ring structure anymore. But this particular space here is a bundle of abelian groups. So the fact that you have a bundle of groups and the twisting is primitive means that you can actually write a product on this side. So this is not a given in general, but for this particular space, we can write a convolution product, and that's how you get the ring structure on the other side. So, right. So what I'm going to sketch now is just how you could carry out this calculation. By the way, I didn't say anything about the twisting here. Let me add that in here. Right. So what is this? This twisting again is nothing mysterious. It's so let's C be the Chern class of the torus bundle G over its flag manifold. So this is C1 of G. Then we can decompose the Chern class, right? Like Ci cup, Ci Ti with respect to the basis of one forms. Then this twisting is just Ci cup Ti. So this is a summing over I, of course. This is H3. All right. Okay, so the idea is to do the calculation on this side. So let me just start by just sort of sketching the calculation for the additive structure. So we want to apply a spectral sequence to this vibration, this trivial vibration. But now we have a choice. We could view this as a torus bundle with G mod T, and the point is you want to view this as a projection onto T hat instead. So you want to view this as a G mod T bundle of a T hat, and apply the spectral sequence in this direction. So this is the Siegel spectral sequence, just an analog of the Serre spectral sequence in ordinary cohomology. So we have a spectral sequence converging to our group. And the second page is the cohomology of the base, which is the dual torus. But now, even though this is a trivial vibration, we have a non-trivial gerb on it. So this non-trivial gerb gives you a local system. And now this is what you notice here is that this is a cohomology, a single cohomology with torus, which is the same thing as a group cohomology of the lattice. So let's see. And of course, we have to work out what the monodromy action is on on this local system. And before doing that, let me tell you, and the definition of group cohomology, one definition is just the X functor. Right, so before going any further, let me explain exactly what the action here is. So first of all, the flag variety is built up with even cells. So first, note that we can restrict to Q equals 0. And we want to know what the action is. T hat on K0, let me just drop to 0. And this is not too difficult to work out. So, right, remember this is the dual lattice. This is spanned by T1 to Tn. So we want to know how these generators act on the K theory of the flag variety. If you let Ci be the Chern class of Li, where Li corresponds to the line bundle given corresponding to this element T. Sorry, this is in this decomposition here, the Ci. Then Ti acts by simply by tensor product. With the line bundle element. And so this is the way to see this is you have the Ti here. It's an element in pi 1 of T, so it's a map from the circle into T hat. So you just pull back the gerb along this map to G mod T across the circle, and when you go around the circle, you can see that the effect of change in the trivialization of the gerb is exactly tensoring by the line bundle given by this line bundle Li. Right, so that's the module structure here for this local system. And also let me just remind you this representation ring of the torus was the group algebra of the lattice, dual lattice. So this is Ti plus minus. And so I should explain this last equality there. We also have an augmentation to make the integers a module under this representation ring. Which sends Ti to 1. So that's the module structure on the ring Z. Right, so before I get into this gory is, well, it's not a gory calculation, it's pretty straightforward, but before I lose everyone, the point I want to raise here is that we want to compute this K3 group. So we work on this side. And the second page in the spectral sequence is manifestly torsion-free. So it's just a cohomology of a torus with a non-trivial coefficient, non-trivial module. And as we'll see in a second, this is very straightforward. You apply the Koszul resolution to compute this. And you also realize very quickly that since the rank of this group is the same as the rank of the rank of the cohomology just by using Chern character, there can be no other higher differentials. So the spectral sequence collapses on the second page. So second page is manifestly torsion-free, and the spectral sequences collapses. So that gives you immediately the additive structure. So
just to be clear, this uses the multiplicativity of the spectral sequence.
No, it doesn't.
No, it doesn't.
Not at all. Yeah. So we'll see in a second. So let's just work out quickly what the second page is, and I'll explain exactly how you get the two steps you need to complete the calculation. So the idea is we want to compute this X group, and it turns out it's easier to apply Poincare duality and compute the Tor groups instead, because you can apply a change of ring spectral sequence, and then the calculation is very straightforward. So steps are, the first step is to apply Poincare duality. So we write the group cohomology of, or the single cohomology T hat with coefficient G mod T as the homology of the degree shift. And which is just a Tor group. That's barely visible. And now to compute this Tor group, we pass from the representation ring of the torus, maximal torus, to the representation ring of the group G. So that's the. So I want to change rings. So of course the restriction map gives you an injection. So we want to apply a spectral sequence that change rings from the representation ring of the torus to that of the group. So we need two pieces of information here. The first is that we're working with simply connected groups, but more generally for torsion-free fundamental groups, this the case here of the flag as a module on the representation ring of the torus can be decomposed very nicely. So it's T modules. And the other piece of information we need is the Steinberg theorem, which tells you that R of T viewed as a module under the representation ring of G is a free module. So again, this requires that the pi 1 of G is torsion is free. G module. So with these two as input for the change of ring spectral sequence, this gives you that this Tor group G mod T is isomorphic to here the integers is again a RG module by precomposing the augmentation with this inclusion. So that's the module structure on Z under R of G. And that's essentially, that's where you would get this is what you would get if you apply, for instance, the equivariant Kunet theorem. So I forgot to mention in the beginning, there was the original proof of Hodgkin in the 60s and the contribution of Atiyah and Araki. But then in the mid-70s, Hodgkin proved a more general theorem, namely the equivariant Kunet theorem. And of course, with that at hand, the calculation gives you this immediately. So you just write K theory of G as G equivariant K theory of G cross G, and then apply the equivariant Kunet theorem. But you can't cheat the devil. To prove the equivariant Kunet theorem, you sort of shift the spectral sequence calculation to proving that theorem, which is of course a more general theorem. So as I mentioned, this is that this proof at no stage is using the equivariant Kunet theorem. So, but if you using the equivariant Kunet theorem, that's where you land. Is that the second page of the spectral sequence is this Tor group of Z cross Z, and then you can use just a causal resolution to compute this thing. So causal resolution for module gives you that this Tor group is just an exterior algebra. So EPQ is get the degrees right here and take P for Q equals 0, and it was of course trivial for K, Q equals 1. So this is just a second page of the spectral sequence, but as I promised, this is all you need to do, since we note that this second page is torsion free, and applying the Chern character, we know that by Hopf's theorem, the rank of the K group equals the rank of the cohomology. So there can be no other high differential beyond this point, because that would imply taking subquotients and lowering the rank. So no differential. Beyond this point. So in other words, the spectral sequence collapses. And no torsion also means that there is no obstruction to splitting the filtration. So no torsion. Yeah. Split the filtration and obstructions. And just keeping track of the odd and even degrees, that gives you Hodgkin's result for the additive structure. So the point is that we don't need to use any classification theorem for groups at all. It goes in one sweep. 2 to the n should take 1. Right. So I keep losing this razor. Right, so that's essentially, so we're not using the multiplicative structure. That's the calculation for the additive structure. And to sum up, for those of you who already fallen asleep, the point is that if you twist this other side, the product, you get an isomorphism. To compute this thing, we want to compute on this side. And then this one we want to view as a G mod T bundle of the torus. And that's essentially the trick, is that the cohomology of a torus is very simple to calculate. it ends up being a calculation of these Tor groups, and this is the main input here. So I should mention at this point is, I don't know if this is useful, this technique, but if you want to, for instance, compute the K groups for non-simply connected groups, particularly when the fundamental group is torsion, this isomorphism still holds. This doesn't require anything about the topology of the group G or the space G. So I guess at this point, this is probably the stage you pick up some issues. So to apply this change of ring spectral sequence, you need these two as input. So this breaks down. So this would be the stage to try to work out the K3 group calculation, where this is not a free module. And I think this could still be a helpful approach to computing K groups for. So yeah, this is essentially the point of this talk, is to promote the Fourier-Mukai transform as a tool in K theory. So it's been used, in spectacular ways in algebraic geometry, but it hasn't really been used very much in K theory. And this is essentially, this whole talk is one application of the Fourier-Mukai transform. All right, so I think I have 10 more minutes or 5 more minutes. 5. All right. So let me just say something about the ring structure as well. So to get the ring structure, we want to equip the twisted K theory with some sort of operation, convolution product. So the insight here is again that the space here, the T-dual, is a bundle of groups. So you can fiber-wise multiply. So you have a multiplication m hat and moreover the gerb, the twisting over the tau, is multiplicative. So one forms on the torus are primitive on the multiplication. So this tau is a multiplicative gerb. Meaning satisfies the following relation. This is pulled back to x cross x hat, and this pi 1 pi 2 are projections. And this is the input you need to define a ring structure. So again, in general, you don't have a ring structure, but in this case, we can actually define the ring structure. So this x hat together with t is if you like, is an abelian group stack. And to write the ring structure, we need that this twisted Poincare line bundle that implements the Fourier-Mukai transform is not just a line bundle, but it's a multiplicative line bundle. So the thing to prove is that there exists a multiplicative twisted Poincare line bundle. And by that means that there is there exists an isomorphism. So there's a diagram that this needs to satisfy. In particular, there's we have a isomorphism, call it lambda. So this, which implements this isomorphism here. M hat T. Such that this Poincare line bundle satisfy the associativity diagram with respect to this isomorphism. So just to spare you the details, this is the input you need to write the convolution product. So this gives us on the twisted K theory of x hat, and it's simply take two twisted K theory elements, and you take the external product, you tensor it with this isomorphism lambda, and you push forward along the multiplication. That's your multiplication here. Let's call this x star y. And the thing to show is that the Fourier-Mukai transform respects the convolution. This is exactly the same way that Fourier transform works in analysis. But the Fourier-Mukai transform in this convolution is the same as tensor, but respects the ring structure, ring operation. So to prove the full Hodgkin theorem, namely the multiplicative part of the theorem, you need to compute this convolution product and then show that it gives you the ring structure. And I think I'm almost out of time, so let me just say that the point is we show that this convolution is simply the internal product on the Tor groups. Is the internal product on the Tor groups, and then again using the causal resolution, you compute the internal product, which is just the exterior algebra multiplication. So causal resolution gives you that this is like algebra multiplication. So sorry, this last part was very sketchy, but that's the strategy for working out the ring structure on the K theory of G. Right, so I think this is a good point to stop.
So the Tor that you get for the twisting, is there a natural sort of bundle of compact operators or matrix algebras that you can write down without passing through Chern classes? I mean, in some of these cases, the Telemann case, for example.
You mean for this tau here, yeah?
Yes. Sort of natural.
It's a decomposable class. So I guess there's yeah, I'm sure you can give a C-star algebra as a continuous trace algebra representative for it. I don't know if there's a sort of a God-given one to
natural because I mean, so these computations in the past were done in it's a sort of equivariant K theory implies usual K theory, that spectral sequence. So wouldn't you expect some of these to have some residual equivariance there?
Yeah, I
would
think
sort of give you a sort of natural candidate for the bundle.
yeah, that would be very nice. Yeah, actually, I'm pretty sure you can. For instance, this class is basic with respect to torus action. So if you, for instance, want to prove the Berlinski-Jang theorem, that if you want to compute just G equivariant K theory of G, so I guess. So you want to sort of enhance this picture with a sort of equivariant Fourier-Mukai transform. I haven't done the calculation. I don't see an obvious obstruction to extend in the picture, at least for commuting abelian group action, or actually just commuting non-abelian group action.
In the audience, we would sort of enlarged K theory to KK theory, and a lot of these computations were done in that case.
Right. Yeah.
So
yeah.
Interesting to know how that sort of how the two tie together.
Yeah, I completely agree. Yeah. I think there should be enhancement to the equivariant Fourier-Mukai transform. Yeah. But you
can
might have to
remove-
set up the geometry
You
correctly.
can remove all the things that Hodgkin did with they were all comparing some computations you did in K theory with some computations you did in cohomology theory, and that was a kind of mess.
Yeah.
Well, not a mess, but it took a long
Yeah.
time.
Well, yeah. This is again using it's essentially the Atiyah-Hertzberg spectral sequence. So it's not evading the cohomology. It's just that the cohomology we're using is a very simple one. That's essentially the insight, but with a non-trivial module, a coefficient. But yeah, I mean, if that would be, I guess the equivariant. The closest I can say answer your remark on your what you said is the equivariant Kuhne theorem is sort of completely avoiding the cohomology. It's just working upstairs.
K theory as well.
Yep. Yes, I think I briefly mentioned is if you have that tool, then it's a one-line calculation.
That's more or less the equivariant K theory for G, or KK theory implies equivariant KK theory for
That's
T.
right. Although I've said, the equivariant Kuhne theorem is also, it doesn't work in, there's some conditions. So for instance, if your fundamental group is finite, it breaks down. It doesn't converge.
Two torsion in pi 1
Yeah.
of G.
Yes, yes. So I think Jonathan Rosenberg had looked at that problem with the two torsion case. But yeah, so that was the remark I made here. I don't know if in the case when the fundamental group is a finite group, whether so this is the in this calculation, this is where the problem occurs. So you want to change the ring, whether this still gives you more sort of easier handle on the problem, then because as you said, the equivariant Kuhne sort of doesn't converge to the right object.
Is it possible to put a twisting on G and try to do the same Fourier-Mukai?
Yeah, I can tell you that was what we wanted to do originally. There's some results. There's this paper by Van Erp and Danzer where by picking they work with reductive Lie groups, and by picking an appropriate level, they get the T-dual to be the Langlands dual. But I think the level, if I remember correctly, all the levels are quite low, so the twisted K groups are all trivial anyway, because the level is much lower than rank. But the short answer is I don't think it's necessarily helpful. But you move a twisted problem to not a twisted. The insight here is that when you have zero twisting on G, you make the dual to be a product. Yeah, that was.
Do you have any other? Another point of view on this construction is the following. We have this free torus action on G, and this gives functions on G a Z to the D grading using the spectral decomposition, and this would be a saturated Hell bundle with fixed point algebra G mod T. So there's some generalized action of Z to the D on functions on G mod T, with cross product being functions on G. So this would be, so you could do the same computation that you would do for cross products by Z to the D. So iterate Pinson-Kolevsky, and I think that's what you have been doing in the second part of your talk, more or less.
Yeah. Sounds.
So this T-duality stuff is just another way of handling these Z to the D cross products, so to speak.
Yeah.
Connect with Con somehow, and
this is the Con-Tom isomorphism in
This Hell bundle point of view, this Z
absolutely,
degrading might be more efficient at getting exactly the right point where this computation goes.
I agree,
If you want to have a twist on G, the question is, would the torus action lift to your twist, to the bundle that you have? If it lifts, I think then you should be able to do something. Whether it helps a lot is another question, but again, you have some Pinson-Kolevsky sequence going on, so you might be able to compute something.
Yep.
But I'm not sure whether a typical twist you like would be torus equivariant. Once you need to go to an RD action, well, then things then you don't have the free action anymore, and then you have more problems maybe.
Right.
Do you have any other questions or comments? No, let's thank the speaker again.